Okay, how y'all doing? We're going to do something a little different. So I'm going to draw a circle again. If you want to draw a circle, a ring of tape is always good. So there's a circle. And what we're going to do is we're going to put a penny sitting on this turntable. Right? So if you've ever played records, you have an idea of what a turntable is. Ask your parents or your grandparents. I don't know. I had one when I was a kid. That was weird. I only got polka music. Most of the time, you shouldn't listen to me. But we'll put the penny at this distance r, which we're going to say is 0.15 meters. Right. And we'll also say that the penny is 5 grams. So we're going to spin this thing up. And it's going to move around the circle. And what we would like to know is how fast is the turntable rotating? So we'll say, what is omega when the penny slips off? And we'll say that the coefficient of friction between the turntable and the penny is going to be 0.3. Let's say, just we'll make a number up. All right, so some between copper and plastic, and this particular plastic. So what I want to do is look at the forces involved on this thing. All right, if we look at it edgewise, this is what we see. We see the turntable, and we see the little copper penny, and it's rotating around and around like that. And the free body diagram we have for this is that we have a supporting force, a normal force by the turntable on the penny upwards. And it's balanced by the weight force that the earth applies to the penny. And then we have a frictional force, the frictional force of the turntable on the penny. Right? And so these two forces are balanced. Right? We can say the sum of the perpendicular forces is the normal minus the weight, and that is 0, because the penny's not going to move up and down, it's going to slide off. So this is going to be that the normal force equals the weight force, and the weight force is always mass times g. Right. So we can also say that the sum of the forces in the circle is going to be just the frictional force. So right when it slips, that's going to be mu times the normal force, which is mu times m times g. But this centripetal force is going to be mv squared over r. So we can rewrite this. We can state that essentially mu mg is mv squared over r, or v squared over r is mu g. All right. But now we can write it in terms of omega. V squared here is, well, V is r omega, so this is r omega squared is mu g, or omega is square root mu g over r. And these are things we can find out. So it will slip immediately after we've done all this forces stuff. Omega is square root 0.3 times 9.8 meters per second squared over, and we'll have r is 0.15 meters. And what's going to happen is we have 1 meter over 1 meter, so that's a radian again. But we're in a square root. We don't know what a square root of a radian is, and we're going to cheat. We're going to slip in 1 meter divided by 1 meter. So that's going to give us another radian. So we'll have square root, and then the thing under here is 0.3 times 9.8 divided by 0.15 is 19.6 radians squared per second squared. So that square root, omega, is 4.43 radians per second. We didn't need the mass here. That's okay. It just happens the pennies should be about 5 grams. Maybe it's the nickel. I can't remember. And actually, I think the penny's 3 grams. That's close enough. We didn't need it because, when we worked on the forces, everything was okay. So you still need to remember your forces. And the trick that we did here was based on V is R omega, or our centripetal acceleration is R omega squared. That was the important thing to convert. That's the thing, is you kind of have to have in the back of your mind these converted, but you also have to have in the back of your mind when they're relevant. Right? There has to be a rotation in order for you to use rotational variables. So we could do other things. So let's check that our stuff makes sense. We would like to know how fast the penny is going as well. So let's make it V is something. Well, we can do V from this. The tangential velocity is R omega, is 0.15 meters times 4.43 radians per second. Anytime you see radians, you can make it as 1 meter over 1 meter and cancel those. So you'll have meters per second. And 4.43, not divided, times 0.15 is 0.66 meters per second. But we have another expression for V, and that's in here. So to make sure that it's right, V is square root mu g r is 0.3 times 9.8 times 0.15, and we'll have meter squared per second squared, square root, so that comes out. So 0.3 times 9.8 times 0.15 square root, V is 0.66 meters per second. It checks out. So there's often a couple of different ways of doing the problem. We could have found V at this step and then converted and found omega, or we could have went through and done the math that we already expected and find omega. So sometimes, depending on what you're asked, you don't have to go as far as you think you have. Anyway, that's a problem that's not unreasonable. It looks daunting because you're like, how am I going to know that? But everything builds on the stuff we've talked about before. And we've talked about circular motion and forces before. You have to be willing to use that in addition to everything else. That didn't do a whole lot of kinematics, but that did sort of the going between translational and angular variables. So let's do another problem. Let's do one more and then we'll call it a day and go home. It is 6 in the afternoon. I have been at the school since 8 in the morning. I've been at this school longer now than I have when you guys actually showed up here. I'm going to have a long day tomorrow and a long day Friday. So please, if you're listening to this early and you owe me work, get it in. What else do we have to do? Okay, so let's do a classical problem. Here we'll have some car tires. These are going to be 20-inch tires on our car. So 20-inch tires means R is going to be 10 inches, is going to be 10 times 2.5 is 25 centimeters. And this car is going to go down the street at a really nice cruising 10 meters per second. And then it's going to come to a stop. And it's going to come to a stop in say 50 meters, let's say. And so what we'd like to know is what is the angular acceleration on the tires? That is a reasonable thing. If you've ever seen dragster, top fuel dragsters, those those things are trying to go from 0 to 300 miles an hour, which is 300 divided by 2.25 is 130 meters per second. They have a huge acceleration, and if you watch the back tires, they deform heavily. And those tires are meant to do that. So on these tires, you could do something like blow the tires out if you stopped too fast. So we're going to try to figure out the angular acceleration here. So there's a couple of different ways of doing it, and I'm going to divide this page in half. And on this side, I'm going to do the angular version, and on this side, I'm going to do the translational version. So this is the thing. If we have something that's rolling along this distance that it stops, then as it rolls, our distance s, the arc length, is also going to be 50 meters. So we can figure out what theta is as s over r is 50 meters over 25.25 meters. That's 50 times 4 is 200 radians. All right, so we'll have theta here is 200 radians. We'll have omega initial is, well, we have to convert it from tangential. So it'll be V tangential over R is 10 meters per second divided by 0.25 meters, and that is 40 radians per second. We'll have omega final is 0 because it's coming to rest. We'll have the acceleration is what we're looking for. We have enough information here, but you could also try to find the time. But what I'm going to look at is say, well, we want the velocities and the distance to tell us acceleration. This is omega final squared is omega initial squared plus 2 alpha theta. And then we're going to solve for alpha. Alpha is omega final squared minus omega initial squared over 2 theta. And that's going to be minus 40 radians per second squared divided by 2 times 200 radians. And what we should get, 40 squared is going to be 1600. Yep. And we're going to divide by 400. And that is going to be 4 radians per second squared. Okay. So you might be thinking, well, how do I know that's true? How do I know what I set up here is true? And this is the thing, is that what's going to happen is we're making an assumption here that this doesn't slip. And so for this thing to travel, say, 1 circumference, each point on the tire has to touch the road at least once, and it has to come back around. So the distance that the contact point goes around the tire is also 1 circumference. And so, that's the condition. This is called rolling without slipping. So as long as we can assume that, we can assume that our angle here is what we claim it is. And so that's what we're doing here. So in the translational case, we're going to work at it the same way. We're going to say, well, what we know is that delta x is 50 meters, v initial is 10 meters per second, v final is 0. We want the acceleration, and the time is unnecessary. Note that it's exactly the same math. We know the same stuff. So we can do v final squared is v initial squared plus 2a delta x. They're the same Actually, I should say delta x is s. So this is going to be 2as. It's going to be the same math relationship, but we're using it with different numbers. So we'll solve for a is v final squared minus v initial squared over 2s is we'll have minus 10 meters per second squared over 2 times 50 meters. Well, 10 squared is 100, and 2 times 50 is 100. So this is going to be minus 1 meter per second squared. Right. And we have a minus sign over here that I keep dropping. I keep dropping minus signs all the time. So now we just say the acceleration is r times alpha. So alpha is a over r is minus 1 meter per second squared over 0.25 meters. That is minus 4 radians per second squared. And it works out okay. So I'm going to make one more video with one more problem, and we're going to do something interesting with it, I think, and we'll go on from there. But this is enough for this video. So please, if you've got questions about this, please email me, let me know. Join the jigsaws that we're doing. If you're listening to this on Wednesday, for whatever reason, then the next jigsaw is Thursday, 3 to 6. This is Wednesday, the 7th of October. No guarantees after that this week.